Okay, we're given a path of a particle, and that is a function of x. Y is equal to 0.5x squared. They also give us the initial conditions that it starts at the origin at t is equal to 0. So we can call this 0, 0. They tell us that the velocity in the x direction is a function of time. It is 5t. They want us to find the distance to the origin, or whatever its displacement is. Oh, sorry. Turn that off. Whatever its position may be. And what the magnitude of the acceleration is, both at 1 second. So I'm going to go ahead and deal with this first. If we start with the velocity definition, it's equal to, in this case, dx dt. Go ahead and drop the vector sign on that. And we can separate variables. The velocity in the x direction dt is equal to dx. We can substitute this 5t for the velocity in the x direction. It gives me 5t dt, and we can integrate. So they told us it started at x is equal to 0, at t is equal to 0. Sum x. Okay, now integrating will give me x, which needs to be evaluated from x to 0, and 5/2 t squared. That'll need to be evaluated from t to 0, giving us x is equal to 5/2 t squared. Now we can plug in 1 foot, 1 second, and find out that it is 2.5 feet in the x direction. So we'll hold on to this for a little bit. We were given the path, so we can find the y coordinate also, but we're going to plug this in later to stuff too. So let's find that y coordinate. Let's just plug back into 0.5x squared. Gives me a y 0.5 times 5/2 t squared, and we need to square that. Plugging in t is equal to 1 second gets you 3.125 feet. Alright, we now have its position vector. It gave us its displacement when we integrate, but it started at the origin, so that ends up being its position vector r. We get 2.5 or 5/2 in the I direction, plus 3.125 in the j direction. And that's all feet. Okay, now it also asked us to find the acceleration and the magnitude at 1 second. And we can find the magnitude of this too, right? It's 5/2 squared plus 3.125 squared. I think this comes out to 4 feet actually. So the length of our position vector r, magnitude is 4 feet. Okay, let's figure out what the acceleration is. Well, they give us the path of y is equal to 0.5x squared. Alright, I'm going to take the time derivative of that. Let's get relationships between position and velocities. Taking the time derivative will give me a y dot on the left side and and x times, don't forget, an x dot. Okay, now let's take the time derivative of that again. We get y double dot, and then I'm going to call this f and this g. Automatically the derivative of g becomes x double dot, and we can say f prime would be 1 times x dot. So putting this all back together, we get x dot squared plus x times x double dot. That's why I said we'd need that x coordinate later. So what does this say? This says the acceleration in the y direction is equal to the velocity in the y direction squared plus the x coordinate times the acceleration in the x direction. Okay, we know x dot is equal to the velocity in the x direction, and we were given that it's 5t, so that's something we can plug in later. At 1 second is 5 feet per second. Okay, well, what about the acceleration in the x direction? That would be x double dot, this thing right here. Well, let's take the time derivative of 5t. Gives us just another 5. It's just coincidence, but it's 5 feet per second squared now. Okay, so we have x dot, we have x double dot. What else do we need? The x coordinate, we already have that. X coordinate is 2.5 feet. So the acceleration in the y direction is then equal to 5 squared plus 2.5 times 5, or 37.5 feet per second squared. Excuse me. They asked for the magnitude. We have the x component and the y component, so we can, excuse me, 5 squared plus 37.5 squared. Get a magnitude. This dominates big time. 37.8 feet per second squared. Thank you.